Hi everyone, welcome back. In this video, we're going to build on what we started in the previous example, talking about layouts, and we are going to switch our thinking a little bit, talking about behaviors. This is also going to be, by the way, the last video in this generative drawing machines module. Okay, so where we're starting here is I've made a copy of the sketch from the previous lesson. This is basically where we're at. We'll do a quick recap at first. We'll do also a little bit of housekeeping, kind of keeping the program as focused as possible. We're going to remove some features, and then we're going to go on to talk about behaviors. What we have right now is we have a layout algorithm that is using an image as a mask, determining where the agents can start in the sketch, right? So I can use different patterns here based on this image to decide where my agents start. And currently, the behavior we've been using the past few weeks has been set the velocity of the agents using Perlin Noise, and more specifically using what's called a Perlin Noise field. Okay, so with the Perlin Noise field, we get objects moving around, right? And their velocity is being influenced by these these vectors that are created by Perlin Noise. And it's a lot of fun. I really enjoy playing with Perlin Noise, but it can get old after a while, right? We can get tired of these wavy lines. And of course, there's a lot of possibilities. We can use this to great effect, but it's nice to do different things. So the lesson today is going to be about talking about behaviors, right? What are some of the other strategies we can start to think about when we're trying to program the motion of our agents? We're going to start with some very simple behaviors that have to do with our drawing surface. Things like, what to do when the agents leave the canvas. Maybe they can just wrap around or something like this. Then we're going to talk about steering motion, where instead of always going straight towards a particular goal, we're going to introduce kind of an intermediate calculation where the agent is going to have to steer, in other words, to turn. Think about when you're driving a car, you're turning the steering wheel. The agent's going to have to turn towards its direction just to create a more interesting range of motion. And then we'll talk about group behaviors, right? Could we influence each other? Could the agents influence each other and their behaviors? And what kinds of things we could program with that? And we'll do some simple examples for all of these. All right. But before we get started, we're going to say farewell to our beloved Perlin Noise here. And so we'll do a little bit of housekeeping in the program. So we are going to get rid of Perlin Noise, and normally I might just leave that stuff in the code, but like I said, we have previous versions saved, and I don't want this program to get too cluttered, so we're simply going to just get rid of the stuff that relates to Perlin Noise, and we're going to start programming different kinds of behaviors. So starting with the settings here, we'll just go through the program and clean it up a bit. So we're going to get rid of the things that have to do with Perlin Noise as a concept. Okay. So we're going to get rid of that from the settings because we're not going to need to zoom or show the Perlin Noise field anymore. And we're not going to draw the Perlin Noise field. So we're going to get rid of this. And we don't need, well, we can keep no fill here. Okay, we're not going to have Perlin field as a behavior anymore. So we're going to add new behaviors over here in a second. And let's see, what else can we delete? We don't need this Perlin field behavior anymore. We can always refer back to our older programs if we want to mess with this. And also have some leftover stuff here. I just noticed we're not using the line thickness in our sketch, so we'll just get rid of it. We'll keep previous position because that's important for drawing continuous lines. We still want to give life for particles. Yeah, that's fine. We'll leave all of that. We'll keep our initial random nudge. This just helps kind of get things going. If we start with no velocity, it's kind of boring. The objects are all static. So this is we'll leave that in there. And what else? That's fine. We're going to keep these different rendering functions and we are good to go. So now if we run the sketch, we end up with this, right? And that's because we have some friction. Let's restart it. Oops. Right. We've got rid of our behaviors. All we got left is our initial nudge we're giving to the agents. Okay? And as I increase friction over here, notice that they just start moving. Okay? And then eventually, if we have no friction, we just have one, they're just going to move. And the only thing that's going to stop them is the end of their life. Okay, so if I increase the max life over here, our agents are just going to move over, and it looks like I just dropped my box of spaghetti on the floor. So this is going to be our starting point here for talking about behaviors. And in fact, we're going to go a little further. We are also going to give ourselves some flexibility here in the interface. Now, because we're going to be talking about behaviors, I kind of want the agents to stick around a little bit longer. So we're going to increase our maximum life here. We're going to make agents that last a little bit longer. We're going to give ourselves a bigger range. And let's make this max life, we're going to bump that up quite a bit, just so that our agents live longer. We're also going to really live more in the almost no friction domain. All right, so let's change our settings here a little bit. Let's go just from 0.9 to 0.1, and we're going to start with no friction as our default state. Okay. Just so we get things, nothing is stopping our agents from moving, right? Fantastic. Oh, that's interesting. So notice, we'll take a couple of tangents here. Notice the friction. If I move my slider, for some reason, that GUI usually does a pretty good job at figuring out the range of numbers, but I don't have anything between 0.9 and 1 here, and I would like to be able to get a lot more granular. So one thing we can do is we can specify here at the end when we add our slider or controller, this actually returns a controller variable, which means we can chain function calls. So I could add a dot at the end of this and use the step command of the controller to define the step value, right? So if I want to have like very fine steps, I could go and override this, and now I have a lot more control over the resolution of my friction. Okay, so that's going to be useful. We can play with that, and because small changes in friction have big changes on the system. Okay? And of course, we can go to no friction. All right. We're also going to, by default, for at least for the time being, we are going to start with not erasing the background. Okay? Just so we see our objects moving. And these tiny little lines here, they're a little bit hard to see. So we're going to switch between different renderers. We're going to have the points and the lines, and right now we also have the shapes or the squares, right? So let's also add to our settings here. Let's add the option to pick a different renderer, okay? So by default, let's say we're going to go renderer. It's going to be render point, okay? That's going to be our default renderer. We're going to give the name here of a function as a string. So if we go back down into our code that we started with, we have a function in there called a render point. Okay. And what I would like to do now is, instead of having to kind of comment out and switch between these different options, I want to be able to just say whatever is in settings.renderer, this is what I want to use to render the agents so that we can interactively try different options that we created. So the way that we can do this is there is a hidden global variable called window inside P5 that we can access. And inside of it, there is an array here where if you use the name, if you use the name of the function you want to call here inside this array, it will return a link, like a handle to the actual function in our program. So we can refer to function names using strings that way. And then the result of this is a function, so we can pass a parameter. Okay, so if we use this syntax, we'll see that this is showing our default renderer, which I changed to render point. Okay, if I put in render line instead, I would render as a line, and if I put in render square, it would put it in as a little square. Okay. Now we have this as a setting, so it would be cool if we could change between them up here. And we can do that using that GUI. Okay, we're going to make that as our first setting here. We're going to say add settings. We're going to add the renderer. So we put in the name of the renderer here. And then if we pass an array of strings, we can put in different words that we want to see. So we could say render square, or maybe like render point, render line, render square. Okay. Now if we run our code and open the controls, we can now choose which function we want to use to render our objects. And we can see it's changing between them. So that can be pretty useful if we don't want to have to restart the sketch every time and just be able to experiment a little bit. So we're going to start with render square as our default, and we're going to make the squares also a little bit bigger for now, just so we can see them. And render square really could be any shape, right? We're drawing little squares here, but it could be any shape, right? A cool thing that could be fun to try is instead of drawing a square, try drawing like a rotated line or something like that, or just even a circle. That could be interesting way also of giving different textures. Okay, moving on. Let's not get sidetracked here. So now what we've done, right? We've kind of streamlined our GUI a little bit. We can choose to erase the background or not, play with the alpha, right? When we hit spacebar, we start a brand new thing, and we can choose different render styles. Okay, so just giving ourselves some choices. Okay, so we'll stick to the squares for now because we want to talk about behaviors. All right. Oh, and one more thing. I'm getting a little tired of this color palette, so just for my sake, I'm going to bring in another color palette here, and we can change. This color palette here is going to look like this. I grabbed it from the same place, coolers.co, just a different palette because I'm getting sick of that one. Another fun one to try as well would be an easy palette to generate by hand would be a black and white palette. That could be fun as well. Something to experiment with when we're doing the drawing machine at the end. There's some cool results that can be had there. But yeah, so for the palettes here, we'll just kind of toggle between them as at will. And we'll use this one just because I'm getting bored of the other one. It's been 3 weeks. Okay. All right, so let's talk about behaviors. Behaviors, basically, the way we're going to think about them in this program are just going to be little functions that we can write that are going to do something to our agent and either change its position or its velocity. And the first kind of simplest way we can start to approach behaviors is we're going to think about kind of like a surface behavior, right? We could say, examples of surface behaviors might be constrain, right? The agent to the surface so that when we reach the boundaries, you turn around or something. Here we're going to implement a behavior just to wrap around so that when our agent leaves the edges of the window, it's going to come back the other side. That can be a very useful way to just kind of keep a small number of agents in play, but generate large numbers of lines because we're essentially just recycling them. They're going to come back into the sketch. So we're not going to implement every possible behavior today. Let's find a blank spot here. Let's call it wrap for wrap around, or I guess we could call it wrap around. And the argument to this behavior is going to be an agent. And the role of that function will be to modify the agent to apply the behavior. So wraparound is a very easy behavior. We're simply going to say, if we exceed the boundaries of the window, we are going to teleport on the other side. Now, instead of just using 0 and width and height as my boundaries, we're going to let the agent kind of leave the window before we do it so we don't have a weird jump effect. So we're going to create a little bit of a buffer, and we can make that a parameter if we want to change it. But by default, we'll make it equal to 100. So that means you have to go 100 past the edges before you teleport back to the other side. So we'll say if agent.position.x, right, is less than minus the buffer, so minus 100, we want to teleport to the other side. We'll say agent.position.x equals width plus buffer. Okay. And we'll do the same thing with the y coordinate, except y is going to be based on height, of course. Go. And then, I don't know why I hit play because we're not calling that code yet. And then we are also going to handle the opposite scenario. So what if we are too far to the right? So we'll say width plus buffer. Then, of course, we want this agent to go back to the left. So we'll say minus buffer. Okay. And again, the buffer is just, we're creating, imagine a space all around the canvas where our agents can go into, and then when they cross that outside boundary is when we want them to teleport. Otherwise, it creates strange visual artifacts, which may or may not be desirable. So position.y equals minus buffer. Okay. And that's it. By default, this boundary is going to be 100. You might want to increase that if you're drawing really large shapes for your agents. You could put in a bigger number over here. We've made it a parameter, just again, to show you some options that you can use to structure your code. So now we have our first behavior wraparound, which is going to be wrap around the edges of the surface canvas. So let's apply this behavior to our agent. We're going to say wrap around agent. So I like this way of thinking about things, and then we'll see they're coming back, right? So they're going to come back, and because we have no friction, they're just going to move forever until they reach their end of life, and eventually they get disappeared, they get removed from the system. And if I hit the letter A, I can seed more agents into it. Okay. So a very simple behavior, but it can be useful to think of in terms of the surface, right? What do you want your agents to do when they reach the edges? The other one, the other obvious one to implement, I will leave that to you as an exercise, would be the bounce when you reach the edge, right? Reverse the agent's velocity. Okay, so our first behavior is we're going to wrap around. Now, the other thing we're going to do is we're going to implement a behavior that we're going to call seek. Okay, so much like we had a few weeks ago, where we kind of followed a particular point, we followed the mouse around. We're going to implement a behavior where our agents can seek a particular location on the screen. That might be useful if, let's say, you create like you use a layout where agents start out on the edges and then they want to seek a goal towards the middle, right? So kind of give them some purpose in life. We're going to program that. However, this time today, we're going to mix it up a little bit. We're going to introduce the idea of steering to our motion sort of formula, our motion mix. And what I mean by this is that currently when we move our agents, the main thing that we do is we just apply forces, right? We just apply a force directly to their acceleration, and that tends to create stuff that mostly moves in a straight line. We got wiggly lines because of Perlin field, always changing the vector direction. But in this context, if we tried to say go towards a particular point and we did not use steering, we would get like pretty straight lines all the time. So we have some options to play around here with when it comes to motion if we introduce steering as a concept. Okay? So the first thing we will do is we will start to program our steering behavior. So the idea of steering is, imagine our agent has like a wheel, like a steering wheel. We're going to turn the velocity, turn the wheels towards a desired velocity, a target velocity, and do this like a little bit at a time. So instead of just applying a direct force onto our agent. So we'll create a function called steering, and the function steering is going to take an agent in, and then it's going to take a direction. This is going to be our desired direction, where we would like this agent to go. And much like when we were programming motion, right, when we were figuring out, okay, my agent is here, this is my position, this is the mouse, I want to know what's the vector between these positions. Remember, we did that a few weeks ago. We used vector subtraction to get the vector between two positions. We can do the same thing with velocities. If I want to know what's the velocity that will take me in a particular direction, and I know my current velocity, and this is maybe where I want to go, if I subtract them, I'm going to get the vector between them. And we can use that as our sort of steering factor. Okay? So the steering factor is going to be a subtraction, except it's this time, instead of subtracting positions, we're going to subtract velocities from one another. Okay, they're all just vectors, but it comes down to like how we interpret them in our program. So we're going to say, okay, this is where we want to go. This is where our agent is going. Let's take the vector between these two, and that's going to become our steering vector. Okay? And then once we have this, we can apply this as a force onto our agent. Okay? Now, if we just take it at face value, these steering vectors are going to be like a little bit intense. So eventually, like, we're going to dampen things down, but for now, let's just leave it as such. And now this, in order for us to test this, right, when we start out here, we want to be able to have a direction that we want to go towards. So building on this, we're going to also implement a simple little behavior. We're going to call it seek. Okay, we're going to seek a particular position. This is a variation on what we've done before. So we're going to seek a target. And the idea is we're going to calculate the target, the vector that's going from this agent to this target, again, using subtraction, same thing. So let's call this target direction. We're going to say p5.vector.sub. Remember when I'm using this syntax here, I'm using what's called a static function call, which means I'm comparing two vectors and then getting a brand new vector as a result. If I use the sub function, say on the direction vector here, and then applied velocity, it would modify one of the two vectors, the one that I use the function on. So I don't want to change these. I just want to get the result of that calculation. So that's when you want to use the static version of the function. Okay. So here we're going to subtract the target where we want to go, right? We're going to subtract to that where our agent is. And we did that in week 3, I think, when we started to talk about agents. So that's going to give us a direction. Now this vector is going to be quite long because it's in coordinate space and screen space. So we are going to normalize it. We're going to make it have a length of 1, just so that we don't get too crazy here. And then we're going to steer our agent toward that direction. Whereas previously we may have simply just applied a force. Okay? And we'll see what the difference is in a second. And we're going to add some options here to vary the amount that we're applying so that we can be a little bit more creative with this. So let's try this behavior. We are going to define a target. So let's call the target create vector. So before we iterate over our agents here, put a comment. Let's just go to the center of the screen for now. Oh, actually, maybe we'll follow the mouse for this example. Okay, just to make it a bit more interactive to test with. And then we will seek agent target. And let's see where we made some errors. So I call this steering. Let's call this steering then. So you can see now all the agents are trying to go, right? They're all trying to go right onto our object, and eventually they all just kind of get lumped in together. Okay, so not the most interesting thing. So what we're going to do is we're going to add some variation to this. We're going to add 2 concepts. First is when we steer, we're going to vary the maximum amount of force that we can apply. In other words, we're going to limit the size of this vector. Okay? And we're going to vary that from agent to agent, just to introduce a little bit of variation. So what that means is we're going to go on our agent here. When we create the agent in the create agent function, we're going to add an attribute to the agent. Let's call this maxSteering. Okay, that's going to be the max steering force that we can apply to this agent. And we'll make this a random number between 0.01 and 0.1. Okay, I'm just using this range from trial and error, but we want these numbers to be small because we're talking about velocities here. So we always tend to want to keep velocities small because when we are messing with applying forces to velocities, it can get out of hand really, really fast. So I like to have these small, and we will apply this. We will limit the length of our steering vector based on settings.maxSteering. So that's the first thing we're going to try. And now this should kind of like respond a little bit differently. Okay? Still not super obvious, but we will get there. The other thing we're going to throw in is that everyone here right now is always moving at a speed of 1. Okay, and that's a little bit boring because we've just normalized our target direction. Okay, if I took that out, you'll see that things are going to get really, really crazy. Okay, so let's find a kind of a good middle ground here. We're going to normalize our target direction, and then we'll also give each agent sort of like a variable speed that they're willing to go to. Just again to create some more variety in our movement. Let's call this max speed. And this is going to be also a random number. And for this one, let's go like between 2 and 6. And you can experiment here with different ranges. And then we can use that number to scale our seek behavior over here. We'll say target direction dot mult settings dot max speed. Okay, so we're just going to go in here and give ourselves some options. Oh, what happened there? Oh, sorry. These are not settings. These are my bad. Small mistake. These are actually attributes of the agent object. So those of you who are paying attention, this should be agent. And because the reason we didn't make this a setting is because I want to be able to vary this on a per agent basis. Okay? So I was like, this is strange. It should be doing something. All right. So now we get a behavior that's more looking something like this. Okay? Let's clear it out. So so in fact, that means our initial steering limit didn't work. So let's go back and try that out. Yeah, so now we can see, okay, I was surprised that they weren't steering as I was expecting before. We can see that they're all now kind of steering with sort of a different amount, right? Some of them have an easier time following the goal. Some of them take longer to turn. That's because the limit is different for each agent of how much they're allowed to steer, kind of like how much of a turn radius their car has. And then the target direction here, this is affecting each agent can be slow or fast, so they have different speeds. Now they're all just kind of following the mouse cursor, and because some of them are going fast and now they have to steer to get there, sometimes they will miss the destination, right? So they will pass it, then they have to turn around and kind of come back, and we can get an interesting behavior out of this, right? So now they're steering. You can see how they turn to follow my mouse. So this steering behavior is going to be helpful because it's going to allow us to create a little bit more dynamic behaviors building on it. When we want an agent to go towards something, instead of just setting its velocity to point that way, now we can tell it to just kind of turn the steering wheel, and that's going to create a lot more curves and interesting little bits of motion. So now they're all trying to follow the mouse, of course. We could decide, instead of following the mouse, maybe they should target the center of the screen, right? So target equals create vector, width over 2. Could be anything. Now they're all going to the center. Maybe we can render them as lines now and not erase the background, and then, oops, yeah, and then start from scratch. And you can see with these behaviors, like now we can start to influence what's happening, or we could add a little bit of friction, right? If we add friction, it just means everything is now slowing down, but we still get the turn at the start. Whereas if we simply just pointed towards it, we wouldn't get any of these things happening. Okay? So again, something that we can keep playing with. Combination of, we can add more elements, we can play with the lifespan. All of these are parameters that can affect what the visual composition is capable of producing. Drawing with points will give us a bigger variety in terms of like textures. Cool. So the same frameworks, right? But we can play with friction and just get like slightly different results. Okay, so this is the steering behavior. Now let's talk a bit for a moment about group behaviors. Okay, so we have a bunch of objects here, and yeah, they can steer. They can steer towards the center. We can also start to think about behaviors where the behavior of the object is going to be influenced by the other objects nearby. In other words, we can start to create not just these individualistic behaviors, but behaviors that are a little bit more based on the group. We're going to program one such example of a behavior where we're going to get the agents to kind of try to keep their distance from their neighbors. They're going to try to stay away from the other neighbors. And the way we're going to do this is kind of the opposite of the seek behavior. We know with the seek behavior, if we calculate a vector, we can calculate the vector that's going from one agent to a target, right? If we do the opposite, right, if we reverse these two, we're going to get the vector that takes us away from a target, right? That's going to be our fleeing vector. And what we'll do is we're going to take a look at an agent's immediate neighbors, and then we're going to sort of average out kind of an arrow that's taking us, the vector that's going to take us away from the most neighbors by using an average. And that's going to be our kind of avoid neighbors behavior. Okay? So let's try this out. We're going to do an example of a behavior that is based on the group. So function here, we're going to say, let's call it avoid neighbors. Okay, why not? And let's use the Canadian spelling. So agent, and here we're going to pass two parameters. We're going to have an agent and a group. Okay, and theoretically, the reason I'm putting it as a parameter, not just relying, even though I have one array right now called group, is that you might have systems where you mix in two different populations, right? So we want this behavior is going to work on an individual agent and then a group that agent is part of. And this could be, in our case, it's going to be just the group array, but this could be any array, really. We could have more than one in a given program, is what I'm trying to say. All right, so how do we avoid our neighbors? Well, first, we have to kind of consider who's nearby. And the way that we can do this is we're going to iterate through the group, and we're going to use the distance function. So this is a pretty brute force approach to neighbors. That means that if we have 1,000 agents in our group, for every agent, we're going to have to check with all 1,000 of them to see how far apart everybody is. And we're going to keep sort of a short list of agents that are within a certain range. Okay, so we're going to define here a radius that our avoid neighbor is interested in. And let's set a default value of 50 here in case we don't end up providing a radius. So that means in a 50 pixel radius around the agent, this is the only other agents we want to consider. So let's write a little for loop here. We're going to use the shorthand syntax because we're not interested in the index of any of these agents. I'm going to call other the other agent of the group. Okay? And remember, the agent is part of the group. So at some point, other and agent will be the same. Okay, but we're going to account for that in a second. We're going to measure the distance. And we're going to say p5 vector dot distance between the position of our agent and the other position. Okay? So this means, again, it's important to emphasize this because if you have a large number of agents, keep in mind this is a much more expensive behavior to calculate. We have to do all the combinations of this agent with everybody else in the system. There are algorithms that will sort of make this more streamlined if you're building very, very large simulations. Things where you could partition the screen into a grid, for instance, and then as you move the agents, you would determine which grid cell they belong to, and then that would allow you to cut down on how many you have to compare with. There's like all kinds of different spatial partitioning algorithms that make this process more efficient. But for this example, we're just using the brute force approach, and it's going to work well enough for us. So we're going to take a look at this distance, and we're going to say, okay, if the distance is less than the radius we specified, then the agent will consider that a neighbor. Okay, it means it's close enough. We will also say if the distance also has to be greater than 0. And the reason why is going to take care of when we compare to ourselves, right? So at some point, these two variables will point to the same agent, and we will get a distance of 0. Or if we have two agents like literally just overlapping, we will ignore that scenario. Okay. Now, what we want to do is we want to add. First, we're going to calculate the vector that's taking us away from that neighbor. Okay, I'm going to call it the flee vector, and the vector that takes us away from the neighbor is the opposite of the seek vector. Okay, so we're going to say subtract. The difference here is instead of subtracting the target, like we want to subtract the position from the target, we are going to subtract the target from the position. We'll say agent.position, and then we'll say other.position. Okay. So the roles are reversed here. If you want to get a vector taking you away from something, it is the second variable in your subtraction. If you want to get the vector taking you towards something, then you will take that destination and put it as the first variable of your subtraction. So we're just flipping them. We'll get the reverse, and now we have a vector that's pointing away from that neighbor we just discovered. Okay? And we're going to do this for every neighbor, and we're going to add all of these vectors up together into one big pile. Now, if you want to average something, you need something to kind of accumulate, to kind of count up the total. And we're going to use that. We're going to create a variable to do that. Because we're adding vectors, this sum is going to be a vector variable as well. And it will start as a 0, 0 vector. Okay. And then we could build up the sum here by saying sum.add flee. Okay. So as we go through all the neighbors and we find some that are close enough, we get the vector that is moving us away from that neighbor, and then we are adding it to our sum total, our running total of flee vectors. Okay, so those all get added up together. And then at the end here, we're going to take the average. Okay? Now, in order to take the average, we need to know how many neighbors did we run into. And right now, we don't have that information. So alongside the sum, we're going to create a count. This is going to start with 0. And if we find a neighbor here, we're going to increase the count by 1. Okay, so that's going to add 1 to the count. The other thing we're going to do, just like in the context here of the seek behavior, right? We normalized the direction and then we kind of kept it smaller because ultimately these are going to become velocities. We're going to do the same thing. We're going to say, because remember, this is the vector. This is the full line going from one object to another object. So we're going to normalize that vector so it has a length of 1, but still points in the right direction. And then we'll go one more step here. That's kind of a cool trick, is we're going to bias the others that are closer to our object. And in other words, we're going to divide that normalized vector by the distance that we just calculated. And if you think about it for a second, what that means is if the distance is short, we're not going to divide by a lot, so it's not going to impact this vector that much. But if we found a neighbor that's just on the edge of that circle, that radius, we're going to divide that flee vector by a lot more because the distance is greater. So that's going to bias towards closer neighbors. Okay, so the flee vectors that are going to have a bigger influence on our overall direction. So the closer somebody gets, the more drastic that we want, the more of an impact we want that flee vector to have. And we can do that by dividing by the distance. Okay, so if you're further away, it's still going to have going to contribute to the sum total, but just less than if you were like right up in my face. Okay? Just kind of an interesting way of thinking about avoiding the neighbors. It's not, you can experiment with this. You can see what happens if you don't. We're kind of just making up behaviors here. Now we'll take the average by, how do you take an average? Well, you take the sum, you divide by the count. Okay? We just want to be a little careful here because if for some reason we had no neighbors, right, then the count is going to be 0, and dividing by 0 is a really bad idea. So we will first make sure that the count is at least 0, meaning we found at least one neighbor, because we could have an agent just by itself over there with nobody around. So make sure we don't divide by 0 here. And then we're simply going to take the average by taking the sum and dividing by the count. This is no different than if you do this with just regular numbers, right? If you take the average of something, you add them all up together and divide by how many numbers you had. We do the same with vectors. We add all the vectors together, and then we divide by the number of vectors we had. And then once we've determined this, we're going to do something similar to the seek behavior. We're going to set the, instead of multiplying it, we're going to set the magnitude because, these vectors here, we've divided them and so forth. We're going to set the magnitude. Set mag just means we're going to set the length to a particular length here. So we're going to say set the magnitude here to be our agent's max speed. Okay. So, and then we're going to steer our agent towards that sum vector. The sum vector being, all things considered, this is the vector that's going to take us away from the most neighbors, with the ones being closer having a bigger influence. Okay. So that becomes our avoid neighbors behavior. And just to recap the concept here, the idea is that we're doing something that's considering the group. Okay, we could have another behavior where instead of moving away from the vectors, the agents we find in the radius, we could use the seek behavior, right? We could try to find, go towards as many, figure out what's taking you closest to the most people. Maybe you don't want to be lonely, or maybe you want to find the center of that neighborhood, move towards that. Okay, so there's all kinds of, or maybe you want to find the closest neighbor, and then once you found that, move towards it, or something like this. So there's all kinds of different behaviors we can imagine that take into account the group, not just the individual. So let's see if we didn't screw this up too much. We'll test it out. So instead of seeking, we will, oops, accidentally hit insert, we will avoid neighbors. So we will pass in our agent and the group as parameters, knowing that, again, we just have the one group in this example, but we could have different ones. We could have layers, right? We could have layers of agents that ignore each other, that only respond to their same kind or something like that. So lots of things we could play with to build on the complexity of these programs. Now, of course, I've made some mistakes, so let's find out what those are. Yes, I call this behavior steering, so I will call this function steering. Of course, you got to be consistent. All right. So you see, this is a little bit slow, right? Because we have a lot of agents, right? We're spawning 1,000 agents here, so let's make our default a little bit less. We're going to spawn 100 instead, just to see what happens. Okay. And maybe I can add a few more into the mix. So these guys are going to move now, but you can see they have this behavior where when they run into each other, some of them are going really fast because they have a high max speed. Some of them steer more easily than others, but generally speaking, they are going to try and move away, right? So if they run into too big of a group, they turn around, they move away from the neighbors. So let's see, let's see what that looks like. If we draw it as a line, maybe we don't erase the background. Turn down the alpha a little bit, right? And then we create some agents in our system. Now we can visualize these lines, right? They start out here. We kept the circle layout, but now they're avoiding each other a little bit, right? And that becomes something we can use to create variation in our lines. This is movement again. Excuse me. This is movement again, but it's different from the Perlin Noise movement, right? We might want these agents to live a really long time, for instance, so that they have more, they stick around for longer. We could increase, their lifespan. I could have made the minimum lifespan too a little bit bigger too. Let me do that. So we have some equivalencies here. Cool. So you get the idea. Or we could see what that looks like with our squares as the thing that's being drawn. Cool. Yeah. So we can paint with these. So now we're getting some behaviors that are different from Perlin Noise. We're just trying to program, what our agents are doing and in what ways could we influence their behaviors. They could seek a particular destination. They could avoid each other. They could follow each other. Lots of experimentations to be done there. All right, we can even combine behaviors together, right? We could say, we can do both, right? We could say seek the center while avoiding your neighbors, right? Let's see what that gives us. Maybe we'll render this as a line, some alpha values, and then let's hit restart here. So let's see what that gives us. Add some more agents. Of course, if you have lots and lots of agents, as I mentioned, things will kind of slow down a little bit. So now we have a mixture, right? We have the behavior we had from avoidance, but they're also trying to get to the center. So we have sometimes conflicting behaviors, and we're just getting the sum total of these applied to our agents. We could play around with adding some friction into the system. See what happens, right? So that by the time they get down to the middle, maybe we'll let them live around a little longer to see what they do, so they can mingle a little bit more, perhaps. creates a little nucleus here in the center. So yeah, all things that we can play with here, and just to change what happens with the system. We can have change the alpha value here quite a bit if we wanted to. Maybe we'll have no friction. And yeah, I could do this for a while. I encourage you to experiment with these systems, try different combinations of behaviors, maybe try to come up with your own behaviors as well. All right. Okay. So pretty neat. Now, the last thing we're going to talk about in terms of behaviors, that's going to go back to maybe just rendering a little bit. I also want to introduce a concept, something that you may want to play with. So currently we're rendering our objects just individually, right? So they're rendered based on their individual location. We can apply the group thinking to our rendering process as well. And we'll do one very quick example where we are going to render, rather than rendering the objects here as individual agents, we're going to connect agents together when they get within a certain distance of each other. Okay. In other words, we're going to render pairs of agents instead of rendering individual agents. Just talk about what that might create. So I'm going to create a function here, call it render pair, and we're going to have agent 1, agent 2. Or you know what? How do we want to set this up? Yeah, let's do that. Let's do agent 1, agent 2. Okay. And the idea here is that we'll get past 2 agents when it comes time to do our rendering, and we're gonna use that to connect agents that are close by, and there could be some really interesting potentials there. So what we'll do is I'll just do it right in here. So we can keep these behaviors up here if we want to for now. We're going to compare every agent with every other agent by writing a for loop. Okay? So now we're already inside a for loop that's iterating through our group of agents. So once we have an agent in our hand, we want to compare it with every other agent. And we can do a little bit of optimization here as well if we wanted to, because we're already inside a for loop. I'm going to create a second counter here, and we're going to count starting from I, okay, which means once we've visited an agent, we're not going to see that agent again in the pair comparison. Instead of starting from 0 every time, we're going to start from I. That's going to cut down quite a bit on the number of comparisons, and it's going to allow us to just have each potential pairs of agents just one time. And the rest of the for loop, we're going to write like the original one. Because we're counting down, we're going to stick with counting down here as well. Remember why we're counting down is because we remove agents when their life runs out here, and we want to always count down when we're splicing from an array while iterating over it. Okay. So look for pairs. I'm going to just do that in here temporarily. So the other agent will be group J. Right? I like to kind of extract it so I don't have to use the square brackets because I find that syntax to be kind of ugly. And then we'll do something similar that we did into the previous group behavior. We'll say measure the distance, right? So we'll say p5 vector distance, agent.position, and other.position. And then we'll say if that distance is greater than 0 and less than a certain radius, let's say 50. Okay. Then we are going to render a pair of agents together. Okay. And render pair is not going to really fit into these functions over here. This is just a little detour. I want to show you just another concept to play with. And let's grab the code that is setting our colors here. Agent.stroke is. We're going to use the agent 1 color as the color, and we'll draw a line between agent1.position.x, agent1.position.y, and the other agent that we receive. Right? So we'll just connect the two with a line for this example and see what we get when we do that. And of course, we have some errors. Let's take a look. Right, agent 1. Okay. So now we get this kind of behavior. And if we don't erase the background, we can get some really fun effects over time happening. So now what happens is we only draw an agent when it's close to another one. And we have access to both of them here. So we could choose to draw them, as a line. We could use the distance. Like we could say, we could draw a circle. Let's do another variation on that idea. We could do we're just going to be wasteful here and measure the distance again. But if we know we're going to do that, we could also add it as a parameter, but doesn't matter. We'll just wasting computation here a little bit, but we can always optimize later. And we could say, let's draw a circle at the agent 1 position. I actually don't know what that will look like. I'm just curious. And use that distance as our radius, perhaps. So now the distance, right, shrinks or increases based on the diameter of the circle. Actually, let's make it ×2 because the distance is really just our radius. If we erase the background, we can get some interesting effects that way. So things that we can play with, right? So this is another way of thinking about group behaviors. I'm going to comment that out and go back to the lines here. Just another way to think about group behaviors, not just in terms of how the agents are being moved. So that's what we did with the avoid your neighbors. This is considering the group as a system where you decide what to draw based on what's happening in the group. That could be another really powerful, really interesting concept to play with for your drawing machines. And then, of course, it's always very fun to see this realized as a composition over time. Oops, I mean to select that. Let's just add some more neighbors. We could create some really interesting compositions that way. Of course, things can get a little bit slow when we got lots of neighbors going, but things will eventually resolve themselves. We're not too concerned about performance here, just sort of creating interesting images. Of course, I can pause it. We could experiment with this. We could take out let's take out the seek the middle, just keep the avoid the neighbors, and then turn down the alpha, erase the background, and then we will add some more objects. Just hit the A key a bunch of times here, and then just let that unfold over time, right? It's got a very Casey Reyes-esque aesthetic to it, or even more so if we switch to a black and white palette, for example. So lots of fun possibilities. Thinking about behaviors, again, a few ways where we can have individual behaviors, we can have group behaviors, and of course, we can think about behavior also when it comes to rendering, right? So we can look at the behavior of the group to decide how we render things. Note that this little render pair I added at the end here, this is useless now, or because we're no longer calling the render function over here. But yeah, just a quick little add-on here before we wrap up. All right, so lots to think about. Please have fun with those ideas, creating your own drawing machines. And yeah, I will see you in the next video when we're going to shift from drawing machines to talking about sound a little bit, but applying some of these similar ideas. I'll see you there.